So I'll just say briefly, yeah, Thilo asked me if I'd like to give this talk, basically because I'm giving a similar talk at EGU next week. I don't know who else is going to EGU. Dietmar, maybe, I think I saw your name somewhere. Oh, Dave, are you going? Yeah, okay, let's see you.
Yeah, I'm going.
Excellent, okay. Yeah, so you don't need to come to my talk. But
very good.
But yeah, hopefully I'll see you in Vienna as well. So the talk is only supposed to be 8 minutes, but this will be slightly longer than 8 minutes, just because I haven't cut out all the stuff yet. And it's also, if you saw my AMOS talk, it's actually almost a duplicate of that. So sorry if you've already seen that as well. But yeah, I'll just talk briefly about these experiments we've run with the ACCESS ESM 1.5 model. So really thanks to Thilo for setting up and running the simulations, working with me. And there's obviously a big group of people involved here. Basically, these long simulations run under net zero CO2 emissions to try and understand climate stabilization processes. So the purpose of these runs is to try and address a bit of a gap in modeling capability from kind of CMIP. So we have policy goals around trying to limit global warming to well below 2 degrees Celsius above pre-industrial levels in line with the Paris agreements. And this implicitly really requires us to achieve net zero emissions and indeed net negative emissions beyond that. But even though we've had this focus on net zero emissions in policy making, countries like Australia have a target for net zero by 2050. The major kind of projections efforts from CMIP6 don't really address this very well. We've got our scenarios. This is just the CO2 emissions pathways for the different major scenarios. We've got a couple that achieve net zero later in the century. But they don't really, most of the models, simulations only go to 2100. So we don't really have a long period of close to net zero emissions. It's hard to really, from these simulations, actually understand the implications of achieving net zero emissions or the effects of delay in achieving net zero. That's not really covered by these experiments. We have other experiments beyond kind of scenario MIP. So for example, ZECMIP, but that's very highly idealized. There will be more new experiments, and there are others like the adaptive emissions model framework that you might have heard about, and that kind of tries to address this problem as well. But the kind of current set of multi-model experiments don't really allow us to really understand the consequences of meeting the Paris Agreement and like the effects of delay in achieving net zero. So essentially, we've got this gap between what our modeling efforts look like and what policymakers need. And we basically proposed new experiments to try and address this gap, to try and understand the consequences of achieving net zero emissions and achieving different global warming levels. So a few years ago, a group of us, including Thilo and myself, proposed new experiments where rather than kind of following the normal CMIP framework of a standard emissions or kind of concentration pathway and a range of global temperature responses, instead different models turn off carbon dioxide emissions at different points in time to try and have a set of constrained global temperature projections and associated climate projections. So we propose these experiments where you turn off emissions at different points in the 21st century and then run forward in time to achieve different global warming levels. This kind of proposal, I think, would help us address kind of policymaker needs. And indeed, we've run these experiments with the ACCESS Earth system model, trying to follow this kind of protocol. So turning off emissions at different points in the 21st century. So CO2 concentrations start to fall. So these are 7 different 1,000-year-long experiments. The yellow to red colored lines. The black line is just historical and SSP 585. So turning off emissions at 5-year intervals in SSP 585, and then running forward and seeing what the global temperature does. And you can see that with these experiments, we achieve a range of different global warming levels, roughly stable global temperatures, very slow warming over the 1,000-year simulations. And we span a range of global warming levels. So using these experiments, we can kind of start to see how does the climate evolve under net zero emissions. So firstly, we've kind of looked at a few kind of large-scale metrics relevant to understanding kind of global climate response. So the top left graph here shows the land-ocean temperature difference relative to pre-industrial levels, 1850 to 1900. And you can see it increases under continued high emissions. And when we turn off greenhouse gas emissions at different 5-year intervals from 2030 to 2060, we see that the land-ocean temperature difference globally averaged starts to drop, but it is still higher than the pre-industrial level. And it's higher if we delay net zero, delay achieving net zero. The top right is the global average precipitation anomaly relative to pre-industrial. So you can see, again, continued increases, but less if we achieve net zero emissions earlier. The bottom left is global mean sea surface temperatures, which continue to rise a little bit under net zero emissions. And the bottom right is the global mean ocean temperature through the depth of the ocean. So you can see that really continues to rise markedly under net zero emissions, much higher levels than it achieves within the 21st century under SSP 585. So you can see that even though global average temperature doesn't change too much, we've got kind of these different responses. Sea ice extent evolves quite interestingly in these model simulations. So the top row shows Arctic sea ice extent in March and September. So trying to capture the maximum and the minimum of the seasonal cycle. And we see in the Arctic, the delaying achieving net zero means reduced sea ice extent. And but not too much evolution under net zero emissions. It kind of stays roughly the same. But for Antarctica, which is the bottom graphs, we see continued declines in sea ice extent, even if we achieve net zero emissions. So the yellow line is turning off emissions in 2030, the red line in 2060, and the dark red line in 2060. And you can see continued declines in sea ice extent all the way through. So even 800-900 years after emission cessation, if we stayed at net zero, in this model, we see continued sea ice extent decline.
Andrew, can I ask something?
Yes, sure.
So you're saying net zero emissions, but is this with a carbon cycle model? So the CO2 concentrations are decreasing, or what?
Yeah, sorry, I should have been clearer on this. So it's run in emissions mode with net zero emissions. So the concentrations do decline. And because it's a fully interactive carbon cycle, we still have uptake of carbon from the atmosphere by the land and the ocean. Thilo can provide a bit more detail on that. But...
Oh, you summarized it pretty well already. It just clarified this is about CO2 only. So we're talking about CO2 emissions, not the other greenhouse, not non-CO2 greenhouse gases.
So what happens to the other ones?
Well, the other greenhouse gas concentrations stay constant. And we made a decision to fix them at their pre-industrial values. So no change in concentrations for the non-CO2 greenhouse gases, and the concentrations for the CO2 is basically determined by the fully interactive carbon cycle. But the emissions are set to 0 for CO2. We don't have the capability to prescribe other greenhouse gas emissions at the moment. Very few models actually do. I think the UK Met Office, they are aiming to have a interactive methane in their next Earth system model. But overall, not many modeling centers have the capability to run with non-CO2 greenhouse gas emissions.
Can I just ask while we're on this slide, so the black is the historical run?
Historical plus SSP 585.
So is it true then in ACCESS you don't really get much Arctic sea ice decline in the model until 2000?
So I think part of the issue, if you look, I'll just go back, I'm sorry, let's go back to the global average temperature. You can see as well, there isn't actually a huge amount of warming either in the global average until kind of the late 20th century. So I think it's partly, I think this is also true with UK ESM, there's kind of, it's not warming up very quickly when there's still that aerosol concentrations.
You'll find that the Arctic temperature, sea ice, and the global temperatures are pretty. There's some correlation plots in the CMIP6 paper that was put out by Sea Ice MIP that correlates where, and the ESM is one of those. It actually doesn't correlate quite as well with the observations as the CM2 model does, but yes, they do correlate in relation to the global temperature, the sea ice decline.
Thank you.
Yeah, so these, just going back to Thilo's point as well, these are quite, they're less idealized simulations than say ZECMIP, which is where we have CO2 increasing in 1% per year and then the emissions cease, but there's no other greenhouse gases. But they also, it's not like a plausible scenario either. That we still have, we're taking SSP 585 and then just turning off emissions, the CO2 emissions at 2030, 2035, and so on. So it's kind of trying to be useful in understanding the consequences of net zero emissions, but it's not like a plausible scenario like scenario MIP kind of aims to.
Are the aerosols being cleaned up? They're following 585?
So they follow 585 and then they stay at 1850 levels.
Correct, they're set back to 1850 levels as well. So you have, there's a lot of things happening at different time scales as well. And if you look at the plot at the bottom right, you can see that initially temperatures actually decline before they start to stabilize. So these are the kind of shortish term effects, and this is the kind of combined effect of setting non-CO2 greenhouse gas concentrations back to pre-industrial, but also aerosols going back to pre-industrial. So one goes the one way, one goes the other way, and the one that dominates, you see the effect here. And we have done some initial experiments around that as well, and it's actually methane that dominates the decline in temperature here. So setting methane back to pre-industrial levels, that has a pretty big impact and is mainly responsible for the temperature decline that we see here in the first 50 years or so. And I guess you could make that more realistic by prescribing concentrations for methane. And methane is a relatively short-lived greenhouse gas, so you could assume that if you have zero or some sort of zero emissions, then it would decline. But this is not even assuming zero emissions because we're setting methane back to a constant level. But I guess you could prescribe something for the other greenhouse gases as well, but then you have to come up with I don't know if you would then use a model to prescribe a trajectory or if you just would make it up. I don't know. But the simplest choice here was just to set them back to a constant level. And that's what most of the idealized simulations do. And I don't even with the proposal for CMIP7, there isn't a better idea on how we could potentially handle this. While talking about these aspects of idealized simulations, I mean, there are other things as well. There is no land use change here anymore. So again, this is something you might want to consider in a more realistic simulation as well. But this is all, it's getting really complicated then. So yes, I guess it's somewhere in between an idealized simulation and a scenario, because we do use initial conditions from a plausible, if you think SSP585 is plausible, from a plausible scenario, but then we have to make choices about how we go forward. That makes sense.
One other comment I'd make about the sea ice in the Southern Ocean, I mean, obviously the Southern Ocean overturning and what's happening in terms of that response is playing a role in terms of those different responses and how much ocean warming is going on. And I don't know if you're going to show them, Andrew, but I think I've seen patterns in the past that Thilo has shown of how much warming is taking place in the Southern Ocean versus what's taking place up in the North Atlantic, and that's obviously having an impact on what's going on in these responses.
Yeah, definitely. I think the Southern Ocean warming just continues all the way through the simulations. I think it's largely responsible for the sea ice extent decline.
Andrew, have you looked at how the deep ocean responds?
Not yet, no.
One thing, like some of that is the point about the Southern Ocean is it's really strongly connected to the deep, and so if you subduct some heat from the North Atlantic in 2100, you'd expect it to sort of influence the Southern Ocean centuries later. So that sort of very slow timescale implies to me the deep ocean's somehow storing some heat, and then and that ultimately has an effect on the Southern Ocean surface. Yeah,
I've been meaning to get around to looking at some of these ones. I think at one point we did get sent an email saying where these were stored, Andy, but I haven't had a chance to go and look at it. But I've seen some outputs that Thilo showed in one of his talks locally at Sarah. But yeah, there's definitely signs that the heat uptake is going on. We know, I think Matt Chamberlain showed some results from the ZECMIP about what was going on in terms of how the overturning circulation was changing in the runs. So yeah, what you're saying is right, that the heat uptake is changing. We know how the ESM overturning circulation is different from the CM2 overturning circulation. So yeah, the heat uptake into the deep ocean, the timescales of that. We know the timescales is really long timescales, and the exchange of that heat was being taking place in the second polar deep water coming to the Southern Ocean, Antarctic bottom water. All those exchange times will be all playing in to where that heat is being uptaken into that ocean and how that's going to play out. But I haven't had a chance to look at it. It's just got too many things on, and I'm only working part-time.
I think one of the really good things with these runs is because they're 1,000 years long, there's just, you can really explore kind of these slow processes potentially. I think we haven't really made the most of them yet in that sense. So the plots I'm showing here are all from this overview paper that's kind of going through, it's been in this discussion mode with system dynamics. But there's a lot of scope for kind of follow-up projects. One thing that Thilo and I have been discussing is looking more at the sea ice changes as well, maybe working with people like Ariane on looking at that. I'll just feel free to just interrupt as we go along, but I'll just show you this next slide, which is just kind of another way of looking at the change in sea ice extents. Using kind of this definition of areas below 1 million square kilometers coverage being essentially sea ice free. I think this is something I've seen in the literature and James Screen has used, for example. This is kind of trying to show the number of sea ice free events per decade in the different runs for the Arctic and Antarctica. Looking at just September, but just look at the seasonal minima in each hemisphere. The bottom row being the historical plus SSP 585, the transient case, and then the different net zero runs. Moving up is delaying emission cessation. And I think what this is trying to show, so going from white to blue is more sea ice free events. And you can see just from the general pattern that in the Arctic, it's really just a function of the amount of global warming. And in Antarctica, there is this kind of time aspect as well, just this delay. It's another way of really showing what the previous plots show. Noting obviously this big caveat about sea ice extent representation in models often being biased. So the ACCESS model, the few papers looking at CMIP kind of a representation of sea ice extent, the ACCESS model is one of the better ones, but it's, I mean, they all have issues, and I think Ariane has kind of illustrated this recently, more focused on Antarctica.
A comment about our model, the ESM is actually not too bad in the summer Antarctic, but it's doing it for the wrong reasons. But that's based on knowing what went into the model, and what went into the model in ACCESS 1.3 period. So that's an earlier knowledge, but yeah, it's not doing it's actually one of the better models in terms of what the ice extent is in Antarctic. But it's doing it, as I said, for the wrong reasons. But I think from the point of view of this slide, that shouldn't actually affect the outcome of what you're trying to say.
It's an interesting problem, because also we obviously want to know more about sea ice extent changes, but it does seem to be, it's obviously concerning if the model processes incorrect or biased. But yeah, that's good to know, definitely. Just another, so there's lots we can do with these simulations, and this is just kind of another way of looking at kind of climate changes in different parts of the world at different points in time in the simulations. So this is a map that's trying to show where locally where we see the peak warming relative to the point when we cease emissions. So in some parts of the world, especially over northern hemisphere land regions, we see, even though as the global temperature doesn't really change too much or slightly warms over the 1,000-year simulations, we see that the land starts to kind of cool off slightly, especially in the northern mid to high latitudes. And what this is really showing is where you've got the lighter colors, the peak warming locally is sooner after net zero emissions, whereas where you've got the kind of darker colors, the red colors, it's still warming throughout the simulations, and you really see this hemispheric contrast coming in, kind of related to what Siobhan was saying before, that the Southern Ocean is just continuing to warm throughout the simulations. We've just picked out a few different locations here to kind of show this. The map is showing an average across the 7 net zero simulations of when the timing is of peak warming. And these graphs for individual cities show the temperature anomaly. That shouldn't say GMST there on the y-axis, but just temperature anomaly locally relative to emission cessation. So you can see, for example, in New York, it doesn't really change that much under net zero emissions, maybe slightly cools. But for a city like Melbourne, or a location like Melbourne, we just have this continued warming, quite substantial, like another degree of warming potentially beyond net zero emissions being realized. So quite different local responses, both over land and ocean areas. Another thing we can do with these models is kind of extract global warming levels. So one thing we tried to do is kind of explore the effects of going through global warming levels versus kind of stabilization at global warming levels at different kind of time periods. So we've got SSP 585 simulations, and the really good thing with doing this with ACCESS is we've got that 40-member ensemble, so we can actually sample kind of rapid warming, 1.5, 2, and 3 degree worlds, and also have quite large samples for 1.5 and 2 and 3 degree worlds at different points in time after emission cessation, and just make comparisons between them. So there's lots more information in the paper about this, but one thing we looked at is precipitation change in the rapid warming versus the stabilization cases. And here on the left-hand side, these are just the changes relative to pre-industrial for summer, northern hemisphere summer, southern hemisphere winter, precipitation in 1.5, 2, and 3 degree worlds. So you can see, obviously, I'm sure everyone in this meeting knows that ACCESS has this quite dry signal over Australia. It really comes out here. And then we've looked at the difference between the early stable and the late stable versus SSP 585 at these global warming levels. And you can see that there's actually quite significant reversal of some of the precipitation changes. So you get quite different projections locally for precipitation if you were looking at the transient or kind of a stabilized case. And actually, yeah, quite significant reversal. So for example, in Europe, where there's very strong drying under SSP 585 in their summer, it gets a lot wetter again under stabilization in the ACCESS model. But this is also similar to findings of recent work by Andrea Dittus, for example, using UK ESM, and under different configuration slightly. So this is just kind of a sample of results. I need to tidy this up before the EGU talk, but yeah, basically what we're trying to show here is that there's a bit of a gap in the existing modeling efforts in terms of understanding the implications of achieving net zero emissions. And this is something that policymakers are demanding, and we can't really get properly from scenario MIP. Hopefully our simulations, along with other experiments that are being run at the moment, kind of offer the chance to better understand effects of different net zero emissions futures. We're finding lots of interesting changes under net zero emissions in temperature, rainfall, sea ice extent, and we haven't looked at lots of other variables yet, but I think there's a lot to explore still. So this is all kind of summarized. There's much more information in the preprints, and there's a QR code as well to the preprints. And yeah, the data is also available on NCI. There's still some processing to be done. But, yeah. Hopefully of interest to people.
Thanks very much, Andrew. All right. So anyone got, I know we were asking questions pretty much throughout the talk, but are there any more questions for Andrew at this point before we move along?
I see, so Rachel and Dave have questions.
So my question was around the precept that you've just shown, and I guess I'm wondering whether the change in aerosols would contribute to any of those differences, and how, whether it's possible or how you might try and disentangle that.
That's an interesting question. We could, we haven't tried to disentangle that. There would be, I suspect there might be some effect, particularly in South and East Asia. Bearing in mind, we're comparing SSP 585 at these kind of global warming levels, especially at the 3 degree level. We're talking about kind of mid to late 21st century. So the aerosol forcings are a bit fair bit lower than they are for the current period in those simulations. They will still be a bit lower in the stabilization runs, but we could explore this. We could look at abrupt forcing simulations, maybe as a comparison, where there's no aerosols. But yeah, we haven't explored this, so it'd be interesting to look at.
Nice. So Dietmar?
Yeah, maybe also related to, I had another question, but since we have this slide up, it looks like that there's a clearly in the SSP 5, 8.5, so in the emission scenario, you have this strong rainfall response in the El Niño region, kind of an El Niño-like increase in rainfall. And then in the stabilization runs, it seems to be reversing. It kind of suggests that the El Niño-like warming is reversing to a La Niña-like. I don't know.
Yeah, we've looked at this a little bit, and it does look like this. There's a few interesting changes. It's really hard in these talks, given their length, to actually.
But it looks like that if you would suddenly stop everything and turn into a stabilization mode, you would switch from an El Niño state into a La Niña state, right?
There's a bit of a mean state change. There's also a change in variability itself, and it kind of looks like so. For example, under stabilization, it looks like ENSO amplitude weakens as well. So it's both a mean change and a variability change happening.
Yeah, but my actually question was about the deep ocean warming. So you showed this upper ocean warming, which was fairly substantial, and I wonder, since you have a carbon cycle model, does this imply that there's a strong change in carbon uptake, or is it carbon release then, or is it in any way realistic? Or
Thilo, do you want to, Thilo's looked at the carbon fluxes and like
yeah, sorry. So for the ocean, it's actually pretty straightforward. The ocean continues to take up carbon, reduced to what it did under SSP 585, but it still continues to take up carbon for a very long time, almost over the 1,000-year time period that we simulate here. But it's kind of reaching an equilibrium again, zero state by the end of the 1,000-year period. So yes, it continues to take up carbon, and that's why we see a decline in atmospheric CO2 concentrations as well, but it's weakening. And then
yeah, but so maybe my question would be that, so you're warming from 4 degrees in the deep ocean to 6 degrees in the deep ocean. So does this 2 degrees of warming in the deep ocean affect the carbon uptake at all? You're saying it still takes up, but it slows down substantially, or?
Yeah. Yes.
Okay. Because of the warming, it slows down and taking up CO2 quite a bit, right? Or
That's total ocean content, not deep ocean content.
yeah, but it's basically the deep ocean, right? The deep ocean is 4 degrees historically speaking, and now you are getting to 6 degrees deep ocean, which to me suggests that this must be substantial impact on the carbon budget, right? I mean,
I think the bigger impact on the carbon budget is going to be just the saturation of the carbon levels in the surface ocean. That's why the carbon uptake reduces, because there's more carbon in there, so the particle pressure differentials are smaller. I doubt it's a temperature effect.
Correct. It's simply the difference in the gradient that drives the carbon uptake.
Yeah, the bottom of the total ocean will not be at 3,000 year 3,000 will not be, or the deep ocean will not be at 6 degrees. It will be still around 2 degrees. 2 degrees, I would imagine. We'd have to look. But the total water column will be, interior of the water column will be much warmer, and the circumpolar deep water will be much warmer.
Okay. I got a question for Julie, or from Julie.
Sorry, I've been waiting for a bit. Could you mind if I chip in here?
Julie, my screen at the top, so I wasn't sure.
Oh, okay. Yeah. No. All right. So yeah, thanks, Andrew. So I know you've got a lot of experiments here, and I'm going to throw more ideas for new experiments. So yeah, but what I'd really like to do with this, if it was me, would be to look at changes to the ice sheets in response to these scenarios. So I'm wondering if you've thought about that, or is there anyone planning to do that? For instance, applying some kind of modeled ice sheet reduction, or plugging these results into an iSheet model, either.
So I haven't really thought much about iSheets so much as sea ice change, but we could talk to. Yeah, I think there are so many things that could be done with these simulations. I guess I've kind of struggled to think of. I'm sure there are lots of things I've not really thought about, and that's kind of one of the areas where I think there's a lot could be done. And yeah, maybe we should have a chat about this actually.
Yeah, so sounds good. In Vienna, maybe. Yeah.
It's probably not very policy relevant, but I guess getting back to those rainfall figures, one of the things that is discussed a lot is a shift of the ITCZ in response to this Southern Ocean warming difference with the Northern Hemisphere. And so I'm just wondering if that might kind of play into the patterns you're seeing. So you're warming the Southern Hemisphere much more than the Northern Hemisphere. That can shift the ITCZ forward.
Yeah, it's again, it's not something we've explicitly looked at. I guess you can kind of pick out a bit of a change here, but it's quite weak. So I know there's been lots of work. I guess there's been more work looking at that in terms of overshoot scenarios. There's a group in South Korea that's been exploring. I think they published a paper on ITCZ movements and like whether they're I struggle to say that word, historical.
Yeah.
But
yeah, I guess Sarah Kang was doing quite a bit on this, and then but it was different in coupled models and simpler models, and so this is a sister model. I don't know if that might be interesting just to diagnose as well, but not really what you're aiming to look at, I guess.
No, but I think again, this is one of these things where there's a lot that can be done with these model runs that we haven't done yet. We've just got this overview paper that is very much skimming the surface, but that's one of these things that could be explored a lot more.
Can I just ask, Julie, are you saying that El Nino pattern in the Pacific at 3 degrees for SSP 585 is more of a shift?
It could be, yeah. It's hard to see, I guess.
Yeah, if you look to the south of the blue bit, it's quite brown. So maybe
I think it's probably less El Nino kind of changes, and maybe just the zonal kind of circulation change.
Yeah.
But yeah, you'd need to
on that, like, so for the late stable, the Southern Ocean was warming late, so it receives its peak warming late from the earlier plot. So it suggests the Southern Ocean is getting really warm, and that should pull the ITCZ further south, right? When you said pole further south, but there's just this big, in that panel C, there's just a big kind of brown line on the equator, which I envisage would be the lower edge of the ITCZ. So for me, it kind of suggests the ITCZ might be moving the other way.
Yeah, it looks very much centered on the equator, doesn't it? So
yeah.
Just I guess thinking maybe digging some more might be interesting.
Yeah, definitely. I think it could be interesting to look into.
Yeah, I think it needs to be explored more properly. But we could look at this. I guess, I mean, obviously all of this is in the context of, the biases in the model itself. And I guess that goes back to Dietmar's question about the El Nino, like mean states shift. Like some of the changes are probably not, or might be due to model bias, but it's still, I think there's a lot of interesting things to be done.
Yeah, I guess this is more an energetic kind of driven thing though, so you'd think that might be potentially better modeled than individual El Nino events potentially, but yeah, it would affect it. So.
All right, so well, thank Andrew again. Thanks very much, Andrew.